So you're able to see the screen?
Yes, sir.
Thank you. So I'm writing on something. So are you able to see? Right?
Yes, sir.
Yes, sir. Yes, sir.
Oh. Okay. Let's wait for 1 minute. Start. I think this week tutorial has went okay. Means something like this is the first tutorial, and there are too many. I think there were too many issues. But by the next week it will be fixed. So you will all will get to know with which TA you are assigned with, and you will get from the next week onwards the appropriate link and all these things will take place. Okay, fine. So let's start with the lecture. Okay, so the last class we have tried to have a had a quick review about some of the very basics, you can say. I think those were not new to you. Okay, and I think we have done with the sufficient number of examples as well. And of course, these are going to be used again and again with different type of problems in probability. Okay. So we will encounter with these these basics again and again, and you will make your understanding more with this by practicing. Okay, right. Now we last time we have defined this definition of random experiment, and I hopefully I have also given the definition of sample space. Okay. So as mentioned the last session as well, so there are two type of possible experiments. One is deterministic and one is indeterministic. So deterministic experiment is nothing but means you know at prior what is going to come. And indeterministic is something like it doesn't mean that we are not we are working with a situation where we don't know anything. Okay, we know some possible things which can be coming, which is possible to come, and then we try to assign some of the mathematical concept with it. Okay, and so-called chance. What is the chance that you will achieve this or you will achieve that? Okay, and you have very real life examples attached with this. So I read tossing a coin or rolling a dice and drawn card from a deck of 52 cards and so on. Okay, there are multiple real life examples exist, and I think there is no need to give here. Okay, so it will come fine. Another interesting thing with the probability, if you have experienced, is the answer of the problem is inside the question itself. If you understood the problem clearly, you will get the answer rightly. And most of the time you will see, means most of the problem what we have encountered so far, they are 1 to 2 line problems. Okay, if you have understood correctly, you can answer in 1 or 2 lines maximum. That's what my experience, but you will also get some experience. I don't know how much you are confident about it. Okay, fine. So random means, I think I just start with now this definition. Just quickly, random stands for randomness. Okay, and of course it has attached with this some 3 bullets here, say A, B, C, and that we have discussed in detail in the last lecture itself. Okay, so so first of all, the first statement of this saying that the set of all possible outcome of the experiment is known in advance. So that's a surety that you know what is going to be the possible outcomes. What are the possible outcomes, not what is. Okay, and then you are going to attach with this. Okay, so among them anyone can come, means that is there is a randomness when you perform that experiment. Okay, you take a box and you place some books, you place some pen, pencil, and so on, those so many objects. Okay, and you note it down on a paper. Okay, and then you just put your hand, something will come out. So that's count, but prior there is only these things are limited. So anything can come randomly, right? Okay, fine. Now we have also given this name, the name attached with this, the set of all possible outcomes, as the sample space. So that we have denoted by, or we are going to denote by omega. Okay, that's it. Okay, so I'm just trying to match with that universal set omega. So this is why here this is omega. Otherwise you can take any S also, is a standard notation. Some of the textbook also follows. Okay, now the second statement will give you this, the outcome of a particular trial of the experiment cannot be predicted in advance. So whatever this outcome of a particular trial means something had happened, means something has been drawn. So that something, if you write down experimentally, means in some certain words, or you can say some, that is a E, that event he means that is the name as event. Okay, means that has happened, means that is an event. Okay, then the third thing is like you want to be fair enough. Okay, right, with the experiment. Okay, so that there is no biasness or unbiasedness. There is no biasness. Okay, right, fine. Fine. Now, so I have the definition of omega and E and also on and so on. Let's move forward then. So I have denoted this sample space omega. So that's a collection of all possible outcomes of a random experiment is called the sample space. Okay. Now, this is a example which you can do yourself quickly. Okay, write down the sample space for each of the following random experiments. If you have a piece of pen and paper, you can write down very quickly. Okay, what will be the omega in the first case? What will be the omega in the second case and third case? Okay, so you quickly write down. Okay, I'm also writing. Okay, you also try. Okay, so it's very quick. I don't think so there is a problem. So when you're rolling a die of six-sided face, okay. So that's here in this case, I think for me is omega is any number 1, 2, 3, 4, 5, 6. Okay. Now the second case is something like it's flipping a coin and rolling a die. Okay, so two things are happening together. Once you flip a coin and then rolling a die. So you have to write down all the possible pairs. So in this case, I think omega, the first can come head, and then the rolling a dice will come with 1. First come head, second can come 2, and so on. 6 till 6, any possibility. What is remaining is the first one could be tail. So you have another 6 possibilities. So this is a very quick to write. Okay, you can write it very quickly. Okay. The third one is something like coin is tossed repeatedly until a head is observed. Means you are now busy. Okay, you are now busy in flipping a coin until a head is observed. So you can write down that quickly as well. Okay, so that here omega in the third case is if it first is head, you will stop. If first is tail, then second could be possibly head. Then third event could be possibly TTH, right? Yes. Then TTH and so on. So means you are entirely busy for the whole day. Okay. And what is the interesting thing here is you will actually get a yes. This is a set which means if you want to connect it with the real analysis, if you have studied, okay, you have studied I think real analysis somewhere, okay, in the calculus part, I think you must have gone through a countable word. Okay, so when a set is said to be countable, is means you should get a 1-1 onto means 1-1 correspondence. Okay, 1-1 onto correspondence between the set of that set and the set of natural number. Yeah. Materialistic things Rohit Rao, you are muted and you are laughing. Yeah. So you can definitely get a 1-1 onto correspondence. Okay. So here you can assign in each entry how a number of tails. Okay. That is an you can say exercise. You can also you can say this is an exercise that you can verify that this set is countable. Okay. This set is countable. Okay. Right. We will do some certain things with this. Okay. Little later. Okay. So the next very obvious definition is event is a set of outcome of the random experiment. That is, so for an example, you can say in this, I will say like in the first case, let's say this is the event getting any number x such that x is less than equals to 3. Means x belongs to natural number and x is less than equals to 3. Or not say y natural number, I should say omega. X belongs to omega such that x is less than equals to 3. So any number can happen. So E is the event 1, 2, 3. So any one of them, if comma, this event is there. So likewise, you can define as many events you like. Okay, it's an example. Hello.
Can you define countable set means once?
Countable set is okay. We say I'm just going to give you the definition, okay, because it will take the whole lecture otherwise. So the definition of a countable set. Okay, so a set, let's say omega, okay, is said to be countable if there is a 1 1 onto map, okay, 1 1 onto map. If there is a 1 1 onto map, I have you can say x from omega to set of natural numbers. So 1 1 onto map, it could be either a from set of natural number to omega, or you can define from omega to set of natural number. Either ways, because whenever 1 1 onto, you have the inverse also exist, and so on. You can talk about this. How would you assign these?
I mean, what does countable set mean? Means definition I got that
Countable. So countable set means it is you can see set of natural number is countable. Can you understand that? Means 1 2 3 4 5 6 7 8. Means you will go on how many times you will end up with some natural number, right? 1 2 3 4, you are taking steps. Okay, that's are countably many. First step, second step, third step, fourth step, fifth step. Okay, so you are going from, like, let's say here DICT to Sargassum Chokri. Okay, so you will count all the means you will, or you can, it is possible to count all the number, all the possible number of steps in form of natural numbers. Okay, forget about this. Forget about fractions. Okay, it means like you take half steps of 1/4 or something. Okay, 1 step, 2 step, 3 steps. So Sargassum Chokri, something like 1,000 steps. But it does not end here. Suppose you extend your area, Sargassum Chokri, some vowel somewhere. So again, still you can count here. Yes, you can count. It may be 10,000. Maybe 10,001 and so on. So the counting will not stop.
How that third example is countable means we don't know when H will come. So
no, see how what are you saying? Yeah, this
in
one.
this third example, coin is tossed repeatedly until a head is observed.
So, but you know how many tail can occur, no? Okay, see, how will you assign this is why I have given you this as an exercise, that see how will you assign a 1 1 onto correspondence between a set of natural number and omega. So you can actually assign the set of natural, means I will say this x of any entry is, say, means like individual entry in omega. Okay, if I denote these as let's take you take, this is a let's say this is E1, E2 and so on. Not E3. Let me mention here E0, E1, E2 and so on. Okay, I think I hope you will get it. The next one I will take as E3 and so on. Okay, so now if I say x of EI is equals to I. Okay, so this is set. So if you minus the one, if you drop, okay, if you drop this first one, if you drop this first one, doesn't matter to countability. Okay, countable of two countable set, union of two countable set is countable. Okay, so so how it is added. So I think you will get how this I is connected is number of tails. Okay, so E1 has number of one, tail is 1, second has 2 tails, third has 3 tails and so on. you will definitely get a natural number where you will add. But how many steps? How many steps you go 10,000 times, tail can occur. Okay,
so
the 10,001th time.
If outcome of event can be represented in any natural number, 1 correspondence, then we can say that set is countable.
Yes. It's
What is
like
the
do you know enumeration? Enumeration. Okay, you are writing it enumerated way. Sequence. Anyways, yeah. Okay, yeah.
Okay.
and sir also as a set of natural numbers is countable infinity. So a countable set is has a number of elements finite or countable infinity,
So
not
there are
uncountable.
two. So there are two ways. It's like countably finite, countably infinite. So countably finite is together merged with finite set. Okay. So countably infinite. Okay, that's the appropriate word for this omega set. This particular third case. Okay, it's a countably infinite. So set of natural number is countably infinite. You can go as large as possible, but what is that? The last that infinity you don't know. Okay, that symbol you don't know. That is a symbol mathematics. Let's say you can say flat or horizontal 8. Okay, that's a simple representation of a very large number, but that still is countable when you go with the it's like 2, 3, 3, 4, 5, 6. Somewhere you will add. So this
Yes,
is
sir.
how this countably infinite is addressed. Okay, I think we can go ahead now. Yeah, fine. Okay, right. So I have given you an example of a certain event. E, okay, is a set of outcomes of the random experiment. That is E subset of omega, right? Yeah, that's a very important concept, like mutually exclusive. Okay, it's completely based on the set theory. Okay, so here two events are said to be mutually exclusive if they cannot occur simultaneously. Okay, for an example, if you go back and check with the first case and this rolling a dice here. Okay, and I say E1 is the event set of all odd number and E2 is the event set of all even number. Okay, so when you roll a dice, either you will get even or odd, but both cannot be good at the same time. Okay, so they are mutually exclusive events. On the other hand, if you take, let's take the even the set of all even number shows up. Okay, and another is let's take the multiple of 3. They are not mutually exclusive because 6 is also an even number. Okay, 6 is a multiple of 3 as well as is an even number. Okay, so I hope you have understood the concept by mutually exclusive. They cannot occur simultaneously. Slowly we'll work more on towards the problem. So okay.
So how about rolling a die and flipping a coin?
Rolling a die and flipping a coin. So that's it. See, you are performing a random experiment. So you are performing a random experiment, like if you are saying that I'm rolling a die as well as flipping a coin together, and then you are writing a sample space, and then based on that you are talking about then outcomes you will note down, like we have done this second case, that sample space is this here. Okay, now you can decide, like first head and another is a or you can take one of the event as where head shows up and rolling a dice and even number. Similarly for tail case, means you can distinguish the cases. So I am I getting your correct question correctly, or if you are performing these two are independently random experiment, like somewhere you are performing a flipping a coin and somebody else is performing a rolling a dice. So for both of you, if you have different sample space, they are completely independent. There's no dependency at all.
Yeah. Okay.
Okay. Yeah. Right.
So are the mutually exclusive?
You can take, yeah, you can yeah, you can say so like that. Because more appropriate word is they are independent. Okay. More appropriate word is they are independent. Okay. Mutually exclusive. Yeah, of course you can say whenever you are saying that random experiment where either you will flip a coin or you are rolling a dice. So then what are the possible outcomes are head, tail, and so. So then if you take flipping a coin and means rolling a dice, they are mutually exclusive. Did you get? No? So in that case, which you are talking about is, I think that the case is when you have the sample space is head, tail, 1, 2, 3, 4, 5, and 6. Okay. So in that case, this and this are separate, so they are mutually exclusive. They cannot occur simultaneously. Either or, means both are not happen simultaneously. Okay. One of the things has been done. Okay. Right. Now, okay. So let's move here now. So now let's define, now once we know the definition of sample space and event, let's define the classical method which you have learned in during your +2 session as well. So whenever you have a sample space is finite, what do you mean by finite is means like number of elements are fixed number of some natural number n. Okay, is fixed, you know, prior. And 2 items, 3 items, or what is going to be. Okay. Now, so I without any delay, I can straightforward go with the final one. Okay. So you have the sample space. Okay, you have the sample space here, omega, which has all W1, W2, Wn are the possible outcomes of a certain random experiment. Okay. Now, this is this notation. Okay, please don't confuse yourself with the absolute value. Okay, this is a when you perform with the set, it means that it's a cardinality somewhere or number of elements inside E. Okay, now what is the important thing here is you are working with this classical method when you have this equally likely outcomes. Okay, when you have equally likely outcomes. So now this is going to be, so that this is a standard way of assigning the probability. Number of favorable cases divided by total number of possible outcomes. Okay. So an outcome, when you will say an outcome is favorable to an event E if it is inside E. Okay. So I don't think so there is any problem. So let's consider the example now, rolling a dice. Okay. So if you consider the example when you're rolling a dice, so your sample space is 1, 2, 3, 4, 5, 6. Now E is the event when you get, let's say, odd numbers, so 1, 3, 5. So what is the probability of E is assigned is number of elements in E is 3 out of 6. Probability number of possible outcomes. So 1/2. Okay. Right? Is that fine? Right? I don't think so. We have to go more for this. You have worked already with this type of problem. Okay. Now, so let's have this example. One more example is here. We have here. Suppose that in a classroom we have 25 students, and let's fix their registration number 1 to 25. Born in the same year, having 365 days. Okay. Now, suppose that we want to find the probability of the event that they all are born on different days of the year. So it's a condition here. Okay. Means all cannot, means any one of them is not born on the same day. Okay. Right. So all are born on different days of the year. Assume that outcomes are equally likely. So each day occur with the probability 1 by 365. Day, if you talk about. Okay. Now, 25 students are there, so you can name them like 1, 2, 3, 4, and so on. Till 25. Okay. With the registration number, you can always sequence. Now, the first one has how many choices? How many favorable to it? 365. All any one of them, 365 is possible. So 365 out of 365. So total possible outcomes are 365. Number of favorable are 365. Okay. So for the first one, you have 365 divided by 365. That's the probability. Now, second one has how many choices? 364. Okay. One day, he cannot born on the same day. Okay. So you have into 364 divided by 365. Now, favorable are 364 and possible outcomes are all possible is 365. Similarly, for third now, he or she cannot born on neither of this day and that day. So 2 are minus, right? 363 into 363 by 365. And so on. Okay. So what you have is 365 minus 25 plus 1 divided by 365. That's it. Okay. Right. So this is what the possibility here. Okay. Right. Now, okay. Now another method which is also maybe familiar with all of you, that known as relative frequency method. Okay. So here what is done is you have independent repetition of a random experiment under identical conditions. So you have to perform it, you can say countably infinite time, you can say. Okay. For an example, again, you are flipping a coin until head occurred. Or what you can say is another, no, then this definition will not be clear. Another way of looking at is, let's say, suppose you flip a coin and note down what is the outcome. Okay. Then you flip a coin, or what you can do is you flip a coin n number of times. Okay. Let's flip a coin n number of times, and you can find out how many number of times head occurs. Okay. How many number of times head occurs? So you have flip a coin n number of times, and you note down E is the event, number of heads. Okay, number of heads. So you noted down how many number of heads will occur, and if you divide it by total number of outcomes, that will be assigned as some frequency here. Okay, total number of head divided by total number of random that random experiment has been done this many number of times, and you repeat it independently infinitely many times. So you will approach this n, so limit n tends to infinity. This ratio, if this ratio is there and this limit does exist, that will be assigned as probability in this case for an event E. Probability of getting head. Okay. I should not say it's a E is the event getting head. Okay. E is the event getting head. Getting head. Okay. And FNE is the total number of heads occurring in the n number of time flipping the coin. Okay. So I just write down n is the number of total number of let me denote n is the number of time flips. Okay. Flips. Okay. Flips, you can say experiment or whatever. Okay. And Fn of E, okay, is number of time. I'm just taking an example, time head occurs. N number of independent repetition of experiment and number of time head occurs, that is the total. Then the probability of E is assigned to B is limit n tends to infinity Fn of E by total number of head. So that will tends to some certain constant limit. That's also questionable. You know how it is difficult to prove. Okay, the existence of a limit. Okay, so but certainly sometime it may also help you in special cases for assigning the probabilities. Okay, but this is not very favorable to all. Okay, so this is why the a proper axiomatic approach needs to be defined. Okay, which will address everything. Okay, right. Okay, so I told number of time, it's not time flips, it's a number of time flips of the coin, of a coin. Okay. Number of time flips of a coin. Okay. We don't okay, because let me, okay, right. So number of time you are flipping a coin. Okay, fine. Right. So this is how this relative frequency method will work. Okay. So I have explained this. So it's and this is a one you can say is a plot drawn from the MATLAB. Okay. After noting down 600 number of n number of trials. Okay. And noting down how many had occurred so far up to 100. When you do up to 200, 300, 400, and so on, and that's it's finally converging to the 0.5 probability of getting head when you're tossing a fair coin. Okay, it's approximately. Okay, it's approximately 0.5. Okay, so you can do this as an exercise at home as well. You take a coin, you draw it, means like 100 number of times, and note it down how many number of heads had occurred. Similarly, you go on till 200, then 300, and try to find out the ratio. Okay, it will go. It should go. Okay, if everything is fair enough, it will go tending to the 0.5. Okay, that you can took as an exercise. Okay, Right. Now, let's define the axiomatic approach for a probability. Okay. So let me once. So this you don't have here. So this is also is not required. And it's also not required. Okay? Because I don't want you to go into the music theory. Okay, let's make it simple. Okay, so let omega be a sample space associated with a random experiment. So a random experiment has been performed, and you noted down all the possible outcomes that we denote by capital omega. So a probability, as we have seen previously, is a function. And indeed, we say this is a set function. Okay. Set function means its domain is a, what is this domain? Its domain is a power set of omega. Means set of all possible subsets of omega. And is a set function defined on this 2 to the power omega. That's a standard notation for defining the power set of omega. Okay, and I hope you are comfortable with the definition of power set of omega, that it consists of all the possible subsets of omega. Okay, so satisfying the following three axioms. So first axiom is non-negativity. Second axiom is accountable infinite additivity. So third axiom will also come. Okay, so first axiom says that whatever subset of omega, or whatever you can say event you take, okay, its probability is always going to be greater than equals to 0. So here I should mention this is omega. Okay, not omega. Not omega. It should be 2 to the power omega. Is a subset of omega. Okay, it belongs to the power set of omega. So probability of any event is going to be either 0 or more than 0, no negative. Okay. Now, second thing is countable infinite additivity. Means you take a collection of mutually exclusive events. Infinitely many you can take, or finitely many. Okay. So if it exists for infinitely many, means it also exists for finitely many. There is no problem with that. So what will happen in that case is probability of union I equals to 1 to infinity ei. You can find out that our probability of all the possible events is nothing but the total probability summation I equals to 1. You take individual probability of each member and then summing up. Okay, so keep in mind that you have an infinite union and infinite sum. Okay, so here the concept which you have learned for infinite series and all, that will come into the picture whenever you are taking a countable infinite collection. I will give an example for that also. Okay, so I hope this also is very clear. Mutually exclusive events means what? In other words, it is like you take any pair, okay, EI and EJ, their intersection is null set whenever I is not equals to 0. This is what we mean. You take any two pairs, they are going to be phi. Okay, null set. Okay. Now, now the third axiom says that probability of the whole sample space is 1. That's obvious, right? That's the third axiom, that probability of omega occurring of all the possible outcome is 1. It's just a certain one of the outcome is surely there's a sure event. Okay. Now you have see, this is from from this first axiom, okay, from this third axiom. So E is a subset of omega. Okay, so it is easy to establish that this you can say this monotonicity property, that probability of E is less than equals to probability of omega. Okay, and so means you take any event, this you can prove that this is going to be the lies between 0 less than equals to probability of E less than equals to 1. Okay, that is very easy. You can prove this monotonicity of this function. Okay, so if A is a subset of B, you can prove that probability of A is less than equals to probability of. That is possible, right? Okay, you can prove that. How you will prove? Okay, how will you prove that? By using this countable infinite activity, you will prove. Okay. Yeah, can you do that? It's very simple. It's very simple. You can write B as A union B minus A. Okay, so probability of B is equals to probability of A plus probability of B minus. Can I write this? Right. So because why? Because the second axiom gives me guarantee that because since A and B minus A are mutually exclusive events, so I can certainly write probability of A union B minus A as probability of A plus probability of B minus A, and it is certainly going to be greater than equals to probability of A. Because of the first axiom that probability of B minus A must be non-negative, greater than equals to 0. There's no chance that it's going to be minus. Okay, so what it tells you together is that that probability is a function. Okay, probability is a function from 2 to the power omega to 0, 1. This range is lies in 0. Okay, right. Now let's move forward now. This is here. So 2 to the power omega is also called the event space. You have all the possible subset of the omega. You can identify them as events. So together you can define as event space. Okay. So I should so 2 to the power omega, and here also 2 to the power omega are called events. That's also fine. Okay. Right. So this is again 2 to the power omega. Now, a countable collection of events is said to be exhaustive. Is said to be exhaustive if this is I should not write here because we are not familiar with that theory. So we say a countable collection is exhaustive if their union will be the whole sample space. Okay, so if what will happen is if union of EIs, I belongs to this sum index lambda is equals to omega. Okay, so a countable collection of event is said to be exhaustive if you have their union will form the full sample space. Okay, right. Now this is an important question. So for a finite collection, you know the classical method to assign the probabilities. If you have a omega is a sample space which has only finitely many members, okay, possible outcomes are finitely many, like rolling a dice or flip a coin and rolling a die together. Still omega is a finite sample space, and you can define and assume that all are equally likely and all these conditionalized conditions. So you can definitely assign the probabilities to each event. Now the question is, what will happen? Is it possible to assign probabilities when omega is countable? So yes, so can anyone answer that? So we have already yes.
Sir, here we are already assuming that all outcomes are equally likely.
Yes, all equal. No, means I'm saying that when omega is finite, you can do so, and you can do that. If you are saying equally likely omega is countable, means you will definitely jump onto the set of natural numbers, and you don't know what is infinity. So each event you will quote it as zero, because 1 by infinity is zero.
Yes.
So, but summing up will not give you the total probability 1. So that will not that will if equal, if you treat equally likely, it will not be a probability function itself. Okay, because probability of whole sample space is natural number, that's natural number, and if you use the countable infinite additivity, you can say that's say and also you will fail to prove the second axiom even, that series will not converge. I think no, each member
Yes,
is
sir.
zero.
So then
So
it is
that's fine.
possible to assign probabilities.
Huh?
So, sir,
Yes, sir.
then it is possible to assign probabilities to all
So what is
subset
the
of.
way?
Sir, breaking the whole omega into small individual events means
Individual events, like say, okay, let me help you here. Let's take omega to be members are like let's take E1, E2, and so on. Individual events means like it is not it's a member. So let me E is denoting for events. Let's take
yes, sir, we can develop a function of probability with the natural number.
x1, x2, x3. Okay, because it's a countable set, you can always enumerate it. That's a very first thing.
Yes.
Okay, yeah.
So sorry, from 2 or 3 in means x1, x2, x3, and suppose natural numbers 1, 2, 3 are related to it, then we can create a function of which gives probability from x1 comma 1, x2 comma 1, and x3 comma 3 to p1,
What
p2,
is
and
that?
p3.
What
Sir,
is
that
that?
will depend on event, means what event is.
Individually, can you do that? Means like suppose I want to get assign the probability of xi event.
Means
Yes, sir,
that
we
will
can do that.
function with, yeah, we can do that.
What is that right side?
Means we will create a function that will depend on input, right? What is input, what is xi. If we take an example of that ending at hex, right?
Okay.
So in that we get function that p of xi equal to 1 by 2 power i.
Hmm.
Yeah, so that how we can create a function and we can define probability for p of xi will be equal to 1 upon 2 power i.
So can I say probability of xi, I'm assigning whatever the object doesn't matter here. So I'm assigning that that's going to be, if we are enumerate after enumerating, I can say 1 by 2 to the power I. Whether it will identify a probability function. See, there are different ways. I'm saying there are different ways to look at it, probabilities.
For that example, we can say that 1 by 2 power I.
Okay.
If our event is stopping when head is occurred, then we can define p of xi equal to 1 by 2 power I.
So what about if other means like instead
they will
of
also
getting head?
Yes.
they will also be functions of natural numbers.
Yes, means we will get different function for different events. For means we will have to find that function.
Hmm.
Because this is countable, so there will be correspondence
Hmm.
to natural number. So the probability function will show some function of natural number in this
Okay,
case
but
also.
so okay, fine. But the thing is here, you are not treating. First of the thing is you are not treating all the events are equally likely. Okay, whether it's a had case or other case. That's a sure. So what is the problem here to assign it as means like irrelevant? Let's take irrespective of that case. What is the problem in suppose I purposefully assign that probability of getting that first x1 is 1 by 2, probability of getting x2 is 1 by 2 square, probability of getting x3 is 1 by 2 cube, and so on. Is there any problem with that? See, there, why you are reaching with 1 by 2 to the power I? Because you are taking the point is too fair and everything is good and getting probability of tail is 1 by 2, getting probability of head is 1 by 2, and then you are using that basic counting principle and all possible things that 1 by 2 into 1 by 2 into 1 by 2 independence of the events, so many things, and then you are reaching this 1 by 2 to the power I. So my point is here is omega is countable. So you can always look this omega as a set of natural numbers. See, what is the meaning of 1 1 onto correspondence? Means, please you see, it is see when you are looking at a map, what is that? How does it help you? Means if you have a 1 1 onto correspondence, or if you have encountered with CS peoples, I think you have encountered with isomorphism and all. Okay, so means you how means 1 1 onto correspondence means that domain and range space means you are having a transformation, you can say. From omega you can go to the set of natural number, from set of natural number you can come back to omega, so always possible, say 1 1 onto correspondence. So you can work with omega as well as set of natural number in the means in the similar way. So this is what the advantage of 1 1 onto correspondence here. Okay, so I don't find any issue here because I can look this omega in a set of natural numbers and I can get any number, set of natural number I can assign with any set of natural number probability, with probability, let's take 4. I will assign with 1 by 2 to the power 4. Getting the number is 100 as 1 by 2 to the power 100. Okay, so 1 1 onto correspondence gives us the opportunity to look at omega and set of natural number equivalently. Okay, not equal. Okay, they are not equal, but you can approach them equivalently. Okay, whatever is happening in this space, similar things you can also find out in the other space. Almost.
Sir, in this example, it is not necessary to be well, all experiments to be equally likely, right?
Yes, not
So
necessary. Means
how?
not. It is. You see, they are not equal. You can't treat them equally likely.
So if the question is that we stop until head is observed, or so how we will find the probability of heads coming equal to 1/2?
How?
How we will define probability of head on coin?
How? See, how will you define the getting a probability of getting a head on a
Yeah.
coin? You are saying
Yes. Yes, sir.
it depends how many number of times you have performed the experiment.
But
How many number of tails has come?
So some else information will be given in question.
Of course.
Oh,
Without that, means like how would you go for it?
no, that means yes, that was I was asking. Okay, okay.
Okay, right.
Yes.
Okay, so with this question, we have the answer that it is possible to assign the probabilities to all subsets of omega whenever omega is countable. Okay, so I'm not going to the uncountable case. You can also look for the uncountable. Okay, can you give me an example of a sample space which is uncountable? Can you give an experiment? Okay, think about it. Okay, think about it when you can have this omega is uncountable. And I hope you understood the meaning of uncountable. Means there is no one to correspondence with this set of natural number and omega. Okay, and you know the large set is set of real numbers. Okay, which is uncountable. So whether you have to restrict with the 1 dimension or 2 dimension, that also you have to think of. Okay, right.
So rolling a dice until 6 is observed.
Until 6 is observed.
Yes.
No, it's still a countability.
It won't be countable. We can't connect one correspondence of omega with natural number.
Why not? Why not?
So 1/6 and 2/6 are different cases if you consider. Means
you took time. Okay.
yeah. Okay.
Okay. Took some time. Okay. And come up means like with an example. Okay. It will. I think it will be countable.
Sir, another example can be set of strings consisting of A and B.
Huh?
Set of all possible strings made out of A and B.
Set no. See. Yes. Wait a minute. One person has posted something in chat box. According to me, is a valid probability function here because the probability function is. Yeah, you are right. So you can see these all three axioms will be satisfied. Boliye. Yes. What are you saying? A and B?
Sir, another example of uncountable set is a set of all possible strings which are made using A and B.
What is A and B?
Sir, any two random characters.
Those characters you can take it from a set of real numbers, right?
Yes, sir.
Correct. Okay. It could be possibly. Now try to answer yourself that whether it is possible to assign probability to them. Okay. So see, there are various ways to look at. Okay, you can look at some geometry as well. Other geometry in R2, in R3. Okay, you can also perform some ideas there. Okay, so come up with your nice examples. We will have a discussion in the next classes. Okay. So this is an interesting question when omega is uncountable. So try to think 2-3 examples. Okay. Right. So yes, another interesting question. So in any probability space, if you have means like we have a probability of the whole sample space is 1. Okay. Now the question is whether probability of A equals to 1 implies A is the whole sample space or not. Now I'm only giving you answer here. The answer is no. Try to think of the example. Okay, that's again an interesting question. So that will also imply that probability of A equals to 0 implies A is a null set or not. Okay, another way of looking at it. Okay, so you have two interesting questions now. One question is when omega is uncountable, whether it is possible to assign probabilities. Another question is whether probability of A equals to 1 implies A equals to omega or not, both sample space. And I hope, that I think both questions are related. I can give you that hint as well. Okay, right? Fine. Okay. So we will do this problem in next session. We have the time. Yeah, we can finish it off. Any question?
Sir, in this second question, if B is that element that we are considering, so if we take B out of omega, then also omega is exhaustive or not?
I don't
Because
understand.
omega is itself exhaustive initially. But if the P of B is 0 and then we take out B.
No, but what if, no, how you can take B is a exclusive from omega? It's not exclusive from omega.
No, B is a subset of omega. P of B is 0.
Okay.
So omega is exhaustive. Omega is always exhaustive, right? And
No, see, if you have, see, you are saying B is a subset of omega with the fact that probability of B is 0. And then, of course, you can write this omega as B union omega minus B.
yes.
And then 1 equals to probability of omega minus B equals to 1. And omega minus B is a proper subset of omega. That's what you are saying.
Yes, so I'm saying that omega minus B is exhaustive or not?
Exhaustible. But why it is required exhaustible? Because B, see, omega minus B means, see, you can always make a difference with the set omega. If B is a subset of omega, still it is valid. And if B is not a subset of omega, even this. What is the meaning of omega minus B? You are just deleting the entries which are matching with B.
Okay.
Okay.
But sir, if
And
probability
two
of
are
B
mutually
is
exclusive. But again, so probability of B is 0. Does it imply that B is a null set or not? So I will ask you in other ways. Then you should not give this example. Then you take B is 1 and then. So you have to come with an example.
Sir, and talking like if we roll 2 dice, the probability, the event where the sum of the number on the dice show up 1. So that can be B. I'm talking like that.
Rolling a dice.
If
But
we
that
roll
is a null
2
set,
dice,
no?
so 1 cannot come, right? Ever.
Okay.
So that
But
will
sample space, but samples that we are talking about a subset of a sample space. We are not talking about, so that is a null set, no? There's no pair, there's no such pair.
okay.
Okay?
Yes, sir.
Yeah. Okay. There are some questions in the chat box. Let us take them. Have occurred during the experiment. No, you are not right, Pinak. If certain thing has not expired, it's not a part of omega. So, sir, I'm talking about, okay, you have to think more about it. Okay. Now, relations. We are considering only countable infinite collection of events. Why are we not considering to be uncountable infinite collection of? See, if you recall the concept of infinite series, okay. So you see uncountable, then you cannot write in the summation. That's so sure. Okay, that's infinite series does not valid there. Okay, any validation is not there, first of thing. Okay, and event to be uncountably infinite collection of mutual experience. Okay, now another is A is a subset of omega. Yeah, that you have to come up with an example, Chira. That A is a subset of omega, A is a proper subset of omega, and probability of A is 1. Or A is a proper subset of omega, but not in the set, probability of A is 0. Either one of them. Think about that example. Okay? Fine.
If probability of A is 0, then why A is in sample space? Means if A is not occurring in event,
This is
probability
what
of
the
A is
beauty of probability. So when you are going to deal with an uncountable omega, okay, then you have to think of. Okay, as long as countability is there, the things will be in shape. Fine. Okay, but when you enlarge your space, the difficulty arises. Okay, like infinite series, you have talked about convergence, divergence. Why? When you have a finite number of sum, there's no problem. Okay, you can do whatever you want with the finite number of sum. You can add them, subtract them, and so on. You can multiply them very easily. But when you have infinite number of things, it is very difficult to address the sum. Okay, so this is why this question is given to you, that when omega is uncountable, is it possible to assign probabilities? If you can come up with an example, yes, here it is. Is this imply the second question? Okay, try to do that. Okay, fine. Yeah, thank you.